Okay. So far, this puzzle has just been a question about a joint probability space. So going from a word problem to transferring this problem uh, into a form when you can get what you know the right answer to be using the uh, math that we've discussed so far. So this includes defining probability spaces, and why isn't this updating? Sorry, my screen isn't. Oh, stupid. Um, Great. So taking a word problem, thinking about what it means probabilistically, and really building up to creating this joint probability space of where the princess is, the choices that the knight can make, and in the end, verifying that the probability that the knight does find the princess is indeed 1/3. Um, Before I continue, are there any questions about this? Steps that we did that didn't make sense? Hopefully you can see everything a little bit easier now. I can try to zoom out and give you a little bit more of a view. This is the meat of it, I guess. Defining this space, the corresponding probability function, defining the proper event that we want to calculate the probability of, and finally just calculating its probability. Okay, can you please type something if you get everything so far? If I lost you somewhere? Great. Then let's go on to puzzle part 2. Go ahead and just copy that. Oh, my screen's jumping like that, sorry. Okay. So, we still have that a knight wants to marry a princess. Ugh. Just rewrite it, man. The princess is in one of 3 caves. Dragons who will eat the prince are in the other 2 caves. Okay. Oh. the prince chooses a cave. Before entering, an honest wizard tells him let's see. Nope, sorry. Just a wizard. Oh. Sorry, I'm bungling this a little bit. It is. This is a cave before entering. Sorry, I really don't know why my screen's jumping around like that. We're entering. Why? Okay. Excuse me. So, similar setup to before. There's a knight that wants to marry a princess. The princess is in one of 3 caves. There's a dragon in the other 2. The prince comes up, sees the 3 caves, and chooses a cave. Doesn't matter. The first cave. And as he's about to go into the first cave, an honest wizard stops him and says, "Prince, there is definitely a dragon in one of the other 2 caves. Maybe cave 2. There's definitely a dragon in cave 2. Let's see. Cave. Say cave 1. Is in one of the other 2 caves. Say cave 2. Should the prince stay with his current choice of cave 1? Should he change his mind and choose cave 3? He does not choose cave 2 because this wizard is honest. He's telling you the truth. So that is the setup. This is the real puzzle. I want to give you guys, let's say 5 minutes, and like actually try to come up with a probability space and an answer, or um, otherwise think about it for a bit. And if you can't come up with anything, just let me know what your intuition is, like what your gut feeling is about this. It could be that he should definitely change his mind. It could be that it doesn't matter. Um, any answer is okay, um, but try to justify it. So I will put up a clock here and give you 5 minutes. Are there any questions before I send you off on this? Does the setup make sense?
I have a question.
Yeah.
It says that Wizard tells them that there is definitely a dragon in one.
Yeah.
Oh, one of the two other kids. I'm sorry, I read it wrong. All right, thank you.
Yeah, and the wizard actually tells him which cave that is. He doesn't just say, "Oh, there's a dragon in one of the other." He names it. He says, you chose cave 1. There's definitely a dragon in cave 2." Or if the prince chooses cave 3, maybe the wizard says, but there's definitely a dragon in cave 1." So the prince chooses a cave. The uh, the wizard names one of the other caves as definitely having a dragon. Any other questions? No? Okay. There's 5 minutes. Just a quick hint on this. This you can frame as a conditional probability. So conditioned on or given that the wizard has revealed some information. Yeah, you can frame the problem in that way. Okay, I see some answers here in the chat. There will always definitely be a dragon in one of the caves you don't choose, so it doesn't matter. Another answer says it matters because the probability changes now, and now he has to make a second decision. And another answer, as long as he didn't choose a cave that the wizard says has a dragon, it doesn't matter, but the probabilities change. Okay, let me just take these in order. So, Royston.
Yeah.
You say it doesn't matter.
Yeah.
Right. Okay, why not?
If I'm reading this correctly,
Mhm.
it seems like the wizard is saying that there will be, like, in one of the caves, there would definitely be a dragon. And that's the case no matter, like, even if the first choice the knight makes is the one with the princess in it, there is definitely a dragon in one of the other caves. I mean, that's the case no matter which cave the knight chooses.
Okay. So okay, great. And Asher, how about I pick you next, just because you sound like you're in agreement that it doesn't matter.
Yeah, so as long as so like if so with your scenario, you're saying he chose a cave and then the wizard tells him a cave that has the dragon?
Right.
So yeah, so as long as he didn't choose cave 2 and then the wizard says cave 2 has the dragon, then it doesn't matter, but like I said, the probabilities will change.
What do the probabilities change to?
Well, so then so then there'll only be two scenarios. You either have princess dragon or dragon and princess.
Okay, so let's say We don't know. We don't know. The prince comes and he's walking into the first cave. Then he's told that there's a dragon in the second cave. And so now there's two choices. So it's a 50-50. That's your thinking?
Yeah.
Okay, great. And Andrew, how about you? No mic. Okay. You say it does matter because the probability changes now and he has to make a second decision. Well, yeah, I mean, he has a choice to change his mind or not. I'm not muted, am I? No. Okay. But you say that the probabilities change now. So what are the probabilities? Now it would be 1/2. Okay. So then does it matter if he changes his mind or not? You guess not. Okay, great. Any other thoughts on this from anyone? One of the dragons, that's right. He doesn't tell you where both the dragons are. He just tells you that there's definitely a dragon in one of the caves that you're not walking into. Okay, so it seems like everybody's in agreement. If you disagree or you're not sure, can you type something? Okay, Mateo's putting a new set. Blow this up. Okay. Each with a 1/4 probability. Okay, and so Mateo is adding some more detail of where these come from. So he's saying that this 1/2 comes from each of those 1/4s, and this 1/2 comes from those 2/4. Right. Okay. Very good. So, This is wrong, which is surprising. It's surprising for a lot of people because it feels like it should be this way. You might even come up with a justification like this, but this is not true, which is why this is a well-known puzzle, I guess, in probability. The correct answer is that he should always change his mind. Given this kind of information, change your mind. It will work out better for you. First, I want to try to give some intuition on why this is. Same setup. We don't know. We don't know. We don't know. Now, imagine here comes along the prince, and he's going into the first cave. He has not met the wizard yet. What's the probability that the prince finds the princess? This is the same as before. One-third. Great. Okay. So conversely, what's the probability the prince does not find the princess? Two-thirds. Perfect. Because these are two disjoint events, right? I mean, he can either find or not find, and this whole thing has to equal 1. You have a third here, therefore he doesn't find him with 2/3 there. Whatever. Okay. So the prince, having made some choice, for example, he's going into the first cave. He knows he only has a 1/3 chance of finding the princess there. Conversely, he knows that he's probably wrong. I mean, he has a 2/3 chance of walking into a cave with a dragon in it. So, in his head, it's helpful to look at it from the perspective of the fact that his first choice was probably wrong. So then, if you're probably wrong about something, and then you get information, the wizard, whatever, tells you that there's a dragon in a cave. This is the extra information. And this is before wizard. Now, we live in a new world, a world where we have some more information. And the question now becomes, how should we update our beliefs? How should we readjust our probabilities? So, the question The real question. This is after the wizard. We'll say, what's the probability of princess, dragon, dragon, given first cave and wizard reveals second cave. Okay, so there's two things that are happening. The prince has made his choice, and the wizard revealed a second cave. Let me pick on somebody who I haven't picked on yet. How about Olga? I don't think I've spoken to you yet. Olga, this is a simpler question. Do you have a mic? Do I mean literally the second cave? Yes, in this case...
Yes, yeah, I have a mic, yeah.
Okay, great. Hold on really quick. Royston, yes, in this case, the wizard literally reveals the second cave. So this is... And you can consider other possibilities, but they all are the same. In this case, we're just imagining that because it doesn't matter, that the prince chooses the first cave, and now the wizard is going to reveal a dragon in one of the other two. Again, it doesn't really matter, so we'll just say that he reveals the second cave. He's going to reveal either the second or the third cave, given that the knight chose the first cave, and so he's arbitrarily deciding the second cave. So in this example, the knight was for sure choosing the first cave, then the wizard for sure revealed a dragon in the second cave. So that kind of leads into my next question for Olga. These two events, the knight choosing the first cave and the wizard revealing the second cave, are these independent?
This one is a revealed second cave. No.
Okay, why not?
I think that's a dependent. No. Is that revealed second? It's a good question.
Okay, if you're not sure, let's check. We have two definitions that we could work with. Do you prefer one definition over the other?
Let's first one, yes. Let's.
The first one. So this is the probability of A and B
yeah.
is equal to the probability of A times the probability of B.
Or B, yes.
Okay. So, okay, we'll call this A and we'll call this B. What is the probability of A?
Probability, right? I don't know.
What's the probability that the knight chooses the first cave?
1/3? Wow.
Right. Yep, 1/3.
Hello? Hello? I don't hear you.
Yes, hello? Oh, you don't hear?
Yes, 1/3?
Yes, 1/3. Great. And what is the probability that the wizard reveals the second cave?
2 seconds?
Yeah. So the wizard is showing that there's a dragon in the second cave. What's
Two, I mean, 2/3, right?
why 2/3?
I don't know.
So here, this is the probability of the wizard revealing a cave all by itself. So because this isn't how to say, it's just the probability that the wizard reveals the second cave. And this is independent of the fact that of whatever cave the knight might choose. There's some cases where the knight or where the wizard can reveal the first cave, some cases where he could reveal the second cave, some cases where he could reveal the third cave. So
1/3.
1/3. Yes, this is also 1/3.
1/3.
Right. Okay.
Yes, yes.
Okay. Does it make sense why it's 1/3?
I don't know. I
Okay.
don't know.
Okay, yeah, if you don't know, ask.
Because it's that's a V. I don't know.
So you're considering, in this case, you're considering just the probability of B. Because this ignores the knight.
Okay.
So ignoring, in the same way that the knight has a free choice over 3 different caves to reveal, when you forget about the wizard. The wizard, when you ignore what the knight's doing, the wizard also has his own independent choice, given that he's ignoring the knight, and there's 3 caves.
Oh, okay.
Right. Hang on a second. Okay.
How about second cave?
How about what?
I mean, no, it's okay. How about second cave here? So first cave and wizard reveals second cave.
Right. So the probability that the wizard reveals the second cave is 1/3. The
1/3.
probability, yeah,
Okay.
because he could reveal the first cave,
Mhm.
or he could reveal the second cave,
Second
or
cave.
he could reveal the third cave.
Okay.
Okay.
Yes.
Now comes the harder part, I guess.
Oh,
This probability, the probability of A and B. So what's the probability that the knight chooses the first cave and the wizard reveals the second cave?
hmm. 2/3?
Why 2/3?
Because first cave is a 1/3.
Okay, so the first cave is 1/3. Okay, and
Second cave it's a 2/3.
what is the second cave? Is 2/3.
No, sorry, it's a 1/3. 1/3. Oh my gosh, I'm confused.
Okay. Right. So the way to think about this is think about 1. A happens. 2, given A, then B happens. Okay? So, and multiply these. Multiply these probabilities. Okay? So you multiply probabilities because this is an and. Okay? Like if I flip, if I have a fair coin and I flip heads, then what's the probability that I flip heads and then I flip tails? So I flip heads, tails. I multiply these two probabilities by each other because one is happening after the other. In this case, first, the prince chooses a cave. So what's the probability of A? This one. What's the probability that the prince chooses the first cave?
It's 1/3, right?
1/3, yeah.
Yes.
Right. So, that's this. The prince has chosen the cave, and there's no wizard. The wizard is not here. And this is a question mark. So that's A. Or this is A happening. The prince chooses one out of the 3 caves. He chooses number 1. That happened with a 1/3 probability. Now, given that he chose the first cave, the wizard will not reveal the first cave. But the wizard can reveal one of the other 2. So given that the prince chose the first cave, what's the probability that the wizard reveals the second cave?
The 2/3?
Why 2/3?
Yes.
Why 2/3?
Because it's the second, it's a 3 caves, it's a 9, right? It's 1 cave, it's a 1/3. Second cave, it's a
Okay. So here,
1/3 too.
still not quite. I'll keep trying. It's okay. So this is the scenario we're in. The knight is going into the first cave. The wizard
Yes.
sees this. The wizard stops him. Now the wizard is going to reveal a dragon. Can the wizard reveal a dragon in the first cave? The prince chooses a cave.
Yes.
Before entering, an honest wizard tells him there's definitely a dragon in one of the other 2 caves. So the wizard, can the wizard reveal a dragon in here? Could this happen?
Yeah.
No.
Why not?
Because
there is no. Okay. Yeah.
because there's definitely a dragon in one of the other 2 caves.
It
Or
doesn't
the 2
matter
other
which
caves.
cave. Yeah.
So the wizard cannot reveal this one because that's not the puzzle. So now the wizard could reveal this cave, or he could reveal this cave. Agreed? So there's 3 caves, one of which the wizard can't reveal anything about. He can reveal something about the other 2.
Okay.
Okay, so what's the probability that the wizard chooses cave 2 and says that there's a dragon there?
Mm, 1/3.
Why 1/3? Okay, let's say that it is 1/3. Then what's the probability
What do
here?
you think? What do you think? Yeah, I don't know this. Yeah.
Okay, well, I mean, I'd like to help you work through it, if that's okay. So the wizard has two choices. Cave 2 or cave 3. He can reveal either one he wants. So what would be the probability that he reveals one or the other? He's going to reveal this cave, or he's going to reveal cave 2 or cave 3.
It's a 1/9.
Okay, if you say it's 1/9 and 1/9, like this?
Yes.
Okay, so then what happened to the other 7/9? Where is this? 1 out of 9 times he'll reveal the second cave, 1 out of 9 times he'll reveal the third cave, and then the other 7 out of 9 times the wizard is going to do what?
I don't know.
Yeah, it doesn't work. That's why it doesn't work, because there's this
Yeah.
whole like world of possibilities that exists outside of space and time. So this is the world.
It's 1/3.
1/3. 1/3. Okay, and so does that mean that this is 2/3? Or is this also 1/3?
This is 1/3. No. First one is gonna be 1/3. Second one is gonna be 2/3. Third one is gonna be 3/3.
2/3.
No, it's a 3. It's a 3 cave is gonna be 1/3, 1/3, and 1/3.
Okay,
No.
You're saying that the wizard could reveal this one with 1/3. The
It
wizard
doesn't
could reveal
matter.
the second one, or the wizard could reveal the third cave. Right?
If wizard start to enter the cave, he doesn't know where dragon in, right? He doesn't know.
I'm not talking about the knight. Right now I'm talking about the wizard.
Wizard.
This is about the wizard.
Oh.
The knight we're finished with. The knight is going into cave 1. Given that the knight is going into cave 1, then comes along the wizard, and he stops the knight, and the wizard is going to reveal a dragon in either cave 2 or in cave 3. So the wizard, maybe I'll keep all these colors. The wizard can choose cave 2 or cave 3. The wizard cannot choose cave 1 because that's where the knight is going. That's not in the puzzle.
Okay.
So given that the knight's going into cave 1, the wizard cannot reveal anything about cave 1. He can reveal something about cave 2 or cave 3. Okay? So far, so good?
So we're not counting this one, first one.
Correct. From the perspective of the wizard.
Oh,
Yeah, the wizard
okay.
does not think about cave 1.
So, okay. It's mean cave, second cave is gonna be one cave, 1/3, right?
If the second cave is 1/3, then what's the third cave?
2/3, right? I mean,
Why do you think that the wizard prefers to reveal cave 3? He's more likely to reveal cave 3 in this scenario. Right? This is a bigger probability, so the wizard is more likely to reveal the third cave?
I think so. I think so.
Okay, why? Why or where is that coming
I
from?
don't know why. I don't know why.
Okay. All right. Here.
I don't know
let me-
why.
Okay, let me give you the answer, and you can see if it makes sense to you. 1/2 and 1/2.
Why is half?
Because the wizard has 2 choices. He could choose the second cave or the third cave. And that's it. He doesn't prefer one over the other. There's 2 choices. He could be flipping a coin. The knight has 3 caves to choose from.
Yeah, this is really confusing. I don't know.
Okay. Think about it this way. Do you
No, it's okay. You said that's 1 second in 1 second because we not touch one first cave. It's mean 1 second, half and half. There is 2 cave that
Yeah.
goes half and half.
yeah.
But it sounds easy when you say. I
Mm.
always think about 3 cave.
Mm.
That's why I always thinking 3 cave right now.
Yeah, and so this is why I want to step through problems with students as well to see where they get mixed up, and maybe if there's a different way to think about it.
So we never count this first one, okay?
Not for the wizard.
Not for the wizard, for the
Yes.
dragon, yes.
For the knight, yes.
Yeah, I mean,
Mhm.
sorry, for the knight, yes.
Yeah. hmm
For wizard,
right.
not. Okay, now
Yeah.
I understand.
Okay.
Thank you.
To just a quick different way of thinking about this. Let's say you have roommates and you have 3 pieces of food. There's spaghetti, there's pizza, there's I don't know, salad. Okay, roommate 1 comes in the kitchen first, and he gets to choose whichever meal he wants. There's 3 plates. Now, roommate 1 he has a 1/3 probability of choosing any of these foods, right? He's the first one in the kitchen, and let's say that he takes the spaghetti. So he takes the spaghetti, he takes the plate, and he leaves the room. Now, roommate 2 comes in, and he has his choice of what remains. And there's only 2 plates here. So for roommate 2, this is why it's a half. It's a similar thing.
Okay, that's a similar thing than that one. I always thought that there is 3 cave in, that's why it doesn't work for me. It's we can't with wizard only 2 cave, not 3 cave. That's
Okay. Good.
thank you.
Sure. Yeah, and in the word problem, it's here. The wizard chooses one of the other 2 caves. So I can see how that could have been missed. Thank you very much, Olga. Oh, wait, I'm sorry, Olga. Sorry, really quick. Let's finish this up. So, okay, all right. So, here,
Yes.
we have the probability that the knight by himself, chooses a cave. We have
Yes.
that the wizard, without knowing the knight, what the knight does, has a probability 1/3 of revealing any particular cave, because he doesn't know about the knight. After he does know about the knight, that, excuse me, changes things a bit. So we have the probability that A, the knight chooses the cave. The first cave is being 1/3. And now, given that the knight chose the first cave, then what is the probability that the wizard chooses the second cave?
Okay, it's still 2 cave. Again,
2 caves. Yes.
still 2 caves. And what next?
What's the probability that the wizard chooses the second cave? The wizard can choose cave 2, or he can choose cave 3. What's the probability that the wizard chooses cave 2?
One, 2. Okay.
1/2.
Yeah.
1/2. Okay, so that's 1/3. This is 1/2, and then you multiply them. Okay.
So in this situation, we have to play wizard and knight.
Yes, on the left-hand side here.
Yes.
For this is wizard and knight together. So A, the knight influences the wizard. If the knight once the knight chooses a cave, then it's like removing a plate. It restricts what the wizard can do. Now the wizard only has 2 choices. If there's no knight, the wizard has 3 choices. But as soon as the knight chooses a cave, now the wizard is forced to only work between 2 things. And so that's what's happening on this left-hand side. Okay, so that's where these numbers are coming from. So this, okay, is 1/9 equal to 1/6?
1/6, yeah.
Are they equal?
No, they're not equal.
Not equal, therefore not independent. Okay.
They are.
All right, that's it. Thank you so much, Olga.
I'm done?
Yes, you're done. Okay.
Thank you.
Sure. Yeah. Okay. All right. Okay. So this is the real question. Okay. We want to find, in the same way that here, the knight choosing a cave restricts what the wizard can do. The knight choosing a cave and the wizard revealing something can change the probabilities of events. So let me bring this down. An aside. All right. All right. Trying to think about the shortest way to get here now. Okay. Let's try something. So, using the definition of conditional probability, which I'll remind you is the probability of A given B is equal to the probability of A and B over the probability of B. So I'll put this to the side and apply it. Call. So let me call this whole thing B, and I'll call this A. And B is actually made up of B1 and B2. Okay, both of those make up B. So just using the equation, this would be the probability of princess, dragon, dragon, and first cave and wizard reveals second cave divided by the probability of first cave and wizard reveals second cave. Okay? Let me use words here, I guess. And okay, all that I'm doing is I'm taking this equation and I'm taking this and just plugging it in. So the probability of A and B is this whole thing, divided by the probability of B. Now, we've calculated the bottom part above. The first cave and the wizard reveals the second cave. We've already calculated that as being 1/6. If you have questions about that, please let me know. I'll try to go through it again. But this is 1/6 from above. And just as a shortcut, this is equal to the probability of princess, dragon, dragon times the probability of first cave and wizard reveals second cave. You know what? I'm just going to start using A and B. I think this is getting really really messy. So sorry, I'm just going to erase this and just use the A's and B's as they are. I'm already writing them here. So here I'll put the probability of A and B over the probability of B. Here, I'll say B1 and B2. It's a nice in between. Okay. Over the probability of B1 and B2. Okay. So the probability that the princess is in the first cave, and the prince chooses the first cave, and the wizard reveals the second cave. One thing to notice is that A and B are independent. For the sake of time, and I won't prove this, but it's easy enough to prove. Okay, you can apply any definition of independence. I'm just saying this to make the calculation go a little bit faster. Therefore, by independence, I can break out this probability. Okay, I can pull out A from the rest. Okay, this way you don't even need to calculate what these are. They cancel out, and you're left with just the probability of A, which is 1/3. Okay. Now this is the probability that the knight chose correctly. The princess is in the first cave. The knight chooses the first cave. And he doesn't change his mind. So the probability of him being correct, ability knight is correct given wizard, is this 1/3. Which means that the probability that the knight is wrong given the wizard is 2/3. I can work more on this. I can delve into this some more. It's actually a really interesting thing about how bad your intuition is when it comes to probability. There's another example we'll go through later in class that reveals this in a different kind of way. But even if you're not very good at the calculations, you should, I strongly believe, exit an undergraduate education understanding that even seemingly simple problems like this one, people's intuitions are not very good at. So either you need to be very careful and very precise, or rely on people who are. And even if it sounds not intuitive, well, I don't know. Hopefully, they have work that you can go through. But this is the shortest way to get to this this answer. Just this screen here. So we're trying to calculate the probability that the knight is correct, given that the wizard reveals something, and that probability does not change. That his first choice was correct. Keep in mind that in this new world, let's see what color I can choose. In this new world now, we've just calculated that the princess, he has a 1/3 chance of being correct if he chooses this first cave, given that the wizard revealed a dragon in the second cave, which means that for sure the knight isn't going to choose the second cave. I mean, that's a death sentence. But he could change his mind, in which case there's two choices, one of which has a 1/3 probability of being correct. We just calculated it. And then the other probability gets absorbed by the other door. So if he changes his mind, he has a 2/3 chance of being correct. This is called the Monty Hall problem. The above is called the Monty Hall problem. There used to be a game show where you choose a door with money behind it. And behind one of them has $1 million, and then behind the others are goats. For whatever reason, goats. This is the way that it's normally presented. A contestant chooses a door. The host will open up a door, revealing a goat. And then he asks the contestant, do you want to change your mind about your which door might have the $1 million behind it? And the answer is yes, always change your mind. Always change it. There's one other way to intuitively think about this. I'll stick with the caves. Let's say there were 100 caves. 100 caves. And the princess is behind only one of them. Then, if the knight chooses the first cave, here your intuition will, or hopefully this gives you more intuition behind what the actual problem is. Take something small and then blow it up into a bigger thing. So the princess is behind only one cave. Now comes along, and now he has a chance, only 1 out of 100 of being correct, right? Like, he's not, his prospects don't look good. Now comes along a wizard who reveals dragons in all caves but 2. Should you change your mind? In this case, absolutely. Right? You had a 99 chance, 99 out of 100, you're going to choose a dragon. Then all of the dragons, in this case, the only one that you can leave open is the one with the princess. So the wizard, 99 times out of 100, will leave the princess behind the remaining cave, because he can't reveal a dragon in it because there's not one there. In which case, 99 times out of 100, in this first case, it makes sense to change. If he were to choose this one, well, then a dragon would have been revealed in the second cave. If he chose the third cave, then the dragon would have been revealed in the second cave. In all of these cases, all of the ones with the dragons, changing your mind makes sense. Okay, so that's another way of thinking about it. Okay. This is a really good problem. I hope that you spend some time thinking about it. And I guess I'll sort of zoom back here a little bit. And sorry, I can't fit all of this on like a single screen. I guess I'll just leave this screen here if you want to look that over. So let's go ahead and take a 10-minute break, and then I'll teach just one last thing about expectation, about random variables. Okay, thanks everybody. Okay, welcome back everybody. So I wanted to emphasize again what this lecture mainly comprised. We were building off of the idea of conditional probability, how to build probability spaces, and that includes joint probability spaces. Without the idea of a wizard, this is just a joint probability problem. So these two worlds are independent of each other, and because they're independent, conditional probability doesn't really help at all, or doesn't really come into play. When you add in a wizard that gives information, then this can change probabilities. This is not the case. First, this idea that there's one of two choices. And this initial idea that everybody shared was being wrong. The reason why it's wrong is, I think, because the perspective is wrong. It's not just that you go through this math. I mean, that's a way to show that things are one way or the other. But it's more about a matter of perspective. And sometimes changing your perspective can lead to different conclusions. In this case, coming at it from the perspective of what are the chances that the knight is right is not the best perspective. It's better to think about what's the probability that the knight is wrong. And given that the knight walked into the thing knowing that it was a random choice and that he was, with a 2/3 chance, wrong, when there's a door that's revealed that leaves, or when there's a cave that's revealed that only leaves two options, then the probability of him being wrong doesn't change. He still has a 2/3 probability of being wrong, which means that by changing, he has a 2/3 probability of being right. If he has a 2/3 probability of being wrong on the cave that he chose, then if he changes his mind, then 2/3 of the time he'll have done the right thing. So again, it can become intuitive, but you just have to think about it and spend some time mulling it over. This is the shortest math way that I know of showing it. You define what it means for him to be right, given the wizard's information. And you find that the probability of him being right is 1/3 if he does not change his mind. Therefore, changing his mind is a 2/3 probability right. Again, this is called the Monty Hall problem. There's plenty of YouTube videos, blog posts, things like this. I mean, this isn't a new problem, but it's the simplest one that I know of that hits home as far as understanding that your intuitions about probability only take you so far. For simple problems, that's great. That's how we spent the first part of this whole course, talking about rolling die, flipping coins, the most simple things that you just sort of know in your gut are one way or the other. This is the first indication where just working off of your gut can lead to problems. So, again, I encourage you to take simple problems, put them in this framework, and then just work through the math. And take medium-sized problems, work out 1 or 2 examples. You don't have to build the whole thing, just parts of it, and make sure that you can follow along. When you can't, please bring these questions to me or to the class, and we can discuss them. Okay, so let's move on to a new topic. Probability distributions, random variables. Here, I'll just give a definition. We don't have much time to get through much else. I will release the homework today. There is one question on expectation that we won't cover by today. This homework will be due next Tuesday at midnight. And we will cover everything that you need to know about expectation in our Thursday lecture. So, just as a motivation for this, probability only concerns itself with events and their probability of occurrence. i.e., a space and a function. Okay? So that's what probability is. There's different theorems, there's different definitions. I mean, we've talked about joint probability, conditional probability, independence, all of these things. But all that this is talking about is what can happen and what's the probability of that happening. random variables allow us to assign numbers to things. Especially to compute averages, variance, etc. Averages is a big one, for hopefully some reasons we'll be able to touch on. A big part of this is something called the law of large numbers. This is sort of the main central pillar of statistics. And that's built by talking about and thinking about taking averages of things, especially averages of averages. So random variables allow us to do that. Example. Let's take the probability space of die. Face 1, face 2, up to face 6. We'll call it a fair die. So the probability of face 1 is equal to the probability of face 6, which is equal to 1/6. So far, we're still in probability world. Okay? These are outcomes. And these... one thing to notice about these outcomes, these possible events, is they can be anything you want. It can be numbers, it can be letters, it can be symbols, it can be abstract things, it can be objects, it can be paintings, it can be movies, anything you want, you can put inside of a set. So the fact that I'm calling it face 1, I'm using the word face in particular because that makes it not a number. Face 1 is not a number. It's a sequence of letters. You can't subtract face 1 from face 2. That doesn't... it's like trying to subtract chair from desk. I mean, it's just nonsense. So, what a random variable maps outcomes to real numbers. That's represented by this R, this thick-looking R. E.g., I'll call it die equals yeah, I'll call this random variable die. Face 1 gets mapped to 1. Die face 2 gets mapped to 2. And on like that, die face 6 goes to 6. Okay, so it takes a set. This is a world, and this is a set. These are elements of the set. These dots are elements. And the set of real numbers, and it maps them. 1, 2, 3, 4, 5, 6. Okay? So that is what, and that is all that a so-called random variable does. It takes a set and just maps them into being some real numbers. So these are numbers that you can do things with. You can add them, you can subtract them, you can multiply them. You can do all of the things that you can do with numbers. These are things that you cannot do in just regular old probability. Probability, you can only talk about things that happen and the probability that those things happen. Random variables, you're talking about numbers. Okay, so that's it. We will pick it up here next time, especially talking about expectation of random variables. Thank you, everybody. I will post the video and homework tonight.